Hi everyone. Today I want to talk about projectile motion. Projectile motion is the motion of projectiles, like this. When that thing is moving through three-dimensional space, it follows a curved path of a particular form. And projectile motion is the study of that motion. And our knowledge of the physics of motion of objects in three-dimensional space can be quite precise. For example, when calculating the motions of things in space, like the motions of the planets around the sun and the motions of other objects, they can be, their paths can be predicted quite precisely. Let me give you an example of that. Here, this is an animated diagram showing the trajectory that the Lunar Reconnaissance Orbiter used to go to the moon. This is a robotic orbiter that was launched from the Earth, and it's now orbiting the moon. It's been orbiting the moon since 2009 or something. And this describes, here's the moon orbiting the Earth. There's the Earth right there. And let's just wait for this to go over again. So it was launched from the Earth on a rocket and sent on a particular trajectory so that it would get to the moon at just the right time when the moon was there in a way to go into orbit. Now they can do little rocket burns along the way to tweak the orbit, but the precision required to plan this trajectory so that it successfully goes into orbit and doesn't crash into the surface, the precision necessary is actually pretty great. And this can be accomplished because our knowledge of orbital mechanics, of basically projectile motion, is pretty advanced. I'm going to do a couple of simpler examples of projectile motion, just things on Earth. Let's say we have an airplane moving along and it has a bomb on it, or let's say it's a care package, not a bomb. And they want to get that care package to somebody that's stranded on the ice in the Antarctic. So they have to drop the package so that it lands pretty near to the building, hopefully without hitting it. So let's say, but the plane is moving, let's say 200 meters per second in a horizontal path, traveling 200 meters per second. If they drop the package, it's not going to land right here, right? It's going to keep moving ahead the way it was when the plane dropped it. Because since Newton's laws of motion are correct, once it's dropped by the airplane, the forces in the horizontal direction are essentially zero. Now there's going to be wind resistance, but we'll ignore that. There's a force in the vertical direction pulling it down, but there are no forces in the horizontal direction, so it'll keep moving with that horizontal speed, moving ahead at 200 meters per second. And it'll begin to accelerate in the vertical direction. So it'll do something like, and hopefully we'll get to there. So this pilot wants to know when to drop the care package in order for the for it to land pretty close to the building so that the people don't have to get out in the ice and walk for miles to go get the package. So let's say this is 500 meters. It's 500 meters above the ground. And he wants to drop it before he gets over the building where the people are in order to make it land in the right spot. So how do we do this? Well, it turns out in projectile motion, the motion in the vertical direction and the motion in the horizontal direction are independent of each other. It's almost like two different problems. If there's forces in the vertical direction but not in the horizontal direction, the package won't accelerate in the horizontal direction, only in the vertical direction. And so the horizontal direction is only affected by horizontal forces. The vertical direction is only, the vertical movement is only affected by vertical forces. So when it's let go, there's no horizontal forces on it anymore because the plane is gone, but there's a vertical force, gravity, and it accelerates downward at the acceleration due to gravity, which is 9.8 meters per second per second. So what I can do is figure out how long it's going to take to cover that 500 meters to get to the ground. And knowing that, knowing that amount of time that it'll take to go from 500 meters altitude to 0 meters altitude, I can say, okay, well, it's going 200 meters per second in the horizontal direction. Given that number of seconds, how far is it going to go? Do you see? And so that tells me how long before being over the house the guy should let go of the care package, if that makes sense. Let me do this. So remember I told you that if an object is accelerating at a constant rate from a standing start, it goes this far in that amount of time if its acceleration has that value, right? So how long would it take to go 500 meters? If the plane is moving horizontally, the thing is motionless in the vertical direction. So it's basically starting from a standing start in the vertical direction. So I can put in 500 meters here. This is 9.8 meters per second. I can solve for t to find out how many seconds it'll take to drop 500 meters. And so this is, t squared is, what, 2 times 500 meters over 9.8. And let me just do this. Actually, I have a calculator today. So 1,000 divided by 9.8, 102, and then take the square root of that. So it's 10.1 seconds. In other words, if an object is 500 meters off the ground and you drop, it's going to take 10.1 seconds to hit the ground. And that doesn't depend on whether it's moving horizontally or not. It's just, that's the amount of time that it takes to go 500 meters when accelerating at 9.8 meters per second squared. Now again, I'm ignoring interaction with the atmosphere. There's going to be air drag, so it'll probably take a little longer than that, but I'm simplifying the problem for the case of illustrating this. Okay, so 10 seconds, 10.1 seconds. Now it's traveling 200 meters per second in the horizontal direction. That doesn't change when the pilot lets go of the care package. So the distance that it goes in the x direction is its velocity in the x direction times that amount of time. 200 meters per second times 10.1 seconds, which is, what is that, 2,020 meters. So this is how far in front whoops. When he's 2,020 meters in front of the house, that's when he lets go of the package. Now in today's lab, you're going to use a simulated projectile motion thing where a cannon shoots a cannonball and you can see how far it goes. I'm going to do one of these calculations with this first. You won't be doing calculations, but you'll just be varying the angle that the cannon fires and seeing how far it goes. But I want to show you a few things about how this simulation works. Let me fire the cannon by clicking that right there. So it traveled in one of these arcing paths and went a certain distance in front of the cannon. Now there's a tape measure up here. I'm going to pull that down and measure how far it went. So there's two little orange plus signs on the tape measure. Put the first plus sign where the plus sign at the base of the cannon is, because that's where the trajectory begins. And then stretch the other one. I don't know if you can see the tape. It'd be hard to see on the video, but I've stretched the tape out to here, and it says 11.2 meters. That's how far the cannonball has gone. Okay. All right, so in the simulation, the cannon was angled up at 80 degrees. the cannonball left the cannon at 18 meters per second, and the distance that it went was 11.2 meters. So I'm going to do some calculations to see where I can see if I can calculate where it's going to land, and see if it turns out to be 11.2 meters. So, all right. Now, in this problem, in the problem with the care package, the plane was traveling horizontally. It had no initial vertical velocity when it dropped, so the package started from a standing start in the vertical direction. That's how I was able to get the time. This time, the cannonball will start moving upward. It'll reach a maximum altitude and then come back down. And I have to find out what that initial velocity is. I can find out what the initial velocity in the vertical direction and the horizontal direction. So to find the initial horizontal and vertical velocities, all I have to do is draw a right triangle. I won't explain why this works, but this is a way to visualize the relationship between the horizontal velocity, the vertical velocity, and the total velocity. This is 18 meters per second. This is 80 degrees. And I can calculate the vertical velocity using a little trigonometry. Hopefully in high school you saw sines and cosines and tangents. The horizontal velocity turns out to be this speed, 18 meters per second, times the cosine of this angle, 80 degrees. And vertical velocity turns out to be this speed times the sine of 80 degrees. Don't worry too much about why this is, but this is one of the things that you learn to do when you take a physics course. Okay, so 18 cosine 80, that's 3.13 meters per second. And 18 sine 8, oops. .7 meters per second. Okay, just from a little trigonometry, I've been able to figure out what is the initial vertical velocity and the initial horizontal velocity. So once again, just like with the care package, I'm going to use, I'm going to figure out with this vertical velocity how long it takes to go up and then back down. Okay? So let me. Okay, so now with the care package, the plane was traveling horizontally, and so the vertical velocity started at 0. It was like the thing was starting from a standing start. Here it's not doing that. It's starting from a running start. And so the equation that I'm going to use is not quite this simple. It has a little bit more stuff. It is has an extra term in it. I'll show you what that means. So it starts at 0 altitude and goes up and then ends at 0 altitude, so the actual distance that it goes is 0. This may seem a little counterintuitive. The initial velocity was, what, 17.7 meters per second, and that gets multiplied by time. And this is going to be the acceleration due to gravity, but since it's down, I have to use a minus 9.8 here. Okay? Now let me take this over to the left side. I'm going to solve for t, find out how much time it takes to do this round trip. I just multiplied the 1/2 on it. Now the negative signs cancel, and one of the t's cancels. So now I just got a simple equation. So it's 17.7 over 4.9 equals that's 3.62 seconds. Okay, so that tells me how long, given this initial vertical velocity, how long it takes to go up to a peak altitude and then back down. And that holds no matter no matter what the horizontal velocity is. If I throw a ball up at 5 meters per second, I can use the same equation to find out how long it's going to take to come back to me. Okay, so that's how long it's in the air, and this is how fast it's moving in the x direction. So I can use those two together. So the distance in the x direction is just the velocity times the time, which is 3.13 meters per second times 3.62 seconds. And that's 11.3 meters. So you see, I was able to almost correctly predict the distance that the thing travels.